Hello, everyone, and thank you all for joining us today on our LTAP and APWA co-branded webinar titled Westerville Takes on a Rising Break Rate Proactively with Data-Driven Water Main Replacement Planning by Kevin Campanella. Kevin is Burgess & Nyepel's utility planning leader and the chair of the National AWWA Asset Management Committee. He also serves on the knowledge team for the APWA Asset Management Committee. He has 30 years of experience assisting utilities with infrastructure management so they can deliver more and spend less. Kevin has led asset management initiatives for utilities with customer counts ranging from 600 to over 2 million. For over 7 years, he was the asset management director at Columbus Public Utilities. He focuses on asset management plan implementation, condition assessment, replacement planning, metrics development, maintenance program development, and emergency preparedness. My name is Josh Ford, and I'm a board member of the Central Ohio branch of APWA and will be moderating today's webinar. If you have any questions, please enter those in the chat box, and we will get to those after Kevin's presentation. And now I will turn the presentation over to Kevin.
Thanks, Josh. I appreciate the introduction, and certainly thanks to you and everybody at APWA Ohio chapter for the opportunity to speak to everybody today, and your help obviously putting the webinar together. So yeah, I'm going to talk about a project that we worked on in Westerville, where they had a rising break rate and made a very conscious decision to address it proactively. As you can see from the slides on the screen, this is a presentation that we first gave last year at PWX in St. Louis, and I'm looking forward to sharing the information that we shared there with you today. So thanks for being here, everyone, and yeah, we'll get started. So I've got a few learning objectives for today. First and foremost is to try to understand the full cost of water main breaks, and that they go well beyond just the direct cost to the utility or the service department that does the repairs. And that'll put in context why proactive water main replacement might be something that's really, really important for you to consider. We'll also talk about how different pipe cohorts behave differently and predictably. So that's important to understand, that if you do want to take on some proactive water main replacement, that you can do it in a very targeted way and get the riskiest pipes out of the ground and be really cost effective. Last learning objective is to understand the importance of using your utility specific data to identify your pipe by pipe risks and what your replacement priorities will be, as opposed to using industry standard values that are out there published by folks like by AWWA and other industry leading societies that have sort of very generic industry standard values that may or may not apply to your utility. Okay, so first and foremost, just to try to put everything in context, we'll talk about the full cost of a water main break. And I just ask you to think about, in your mind right now, how much an average water main break costs. And for most utilities in Ohio, I can say, based on my experience when I was with the City of Columbus, from a financial standpoint, that cost ranged anywhere from about $3,000 up to $5,000 for the direct costs. This is what I'm going to share with you here is based on a study that was put together by the Water Research Foundation. It was study number 4451, I believe, was the study. And the attempt was to try to determine what all the other costs of a water main break are beyond just the cost of the utility. So this is based on data that was gathered from utilities around the country. When I was with Columbus Public Utilities, we participated in this study, and I know that they've got breaks from around the US, including some breaks in Alaska. But what you see here is the cost of a break, the total cost of a break on the x-axis, and then sort of, you know, the percentile, 50th percentile, 90th percentile, all the way up to the max. And the color-coded bars here represent in dark blue the direct cost to the utility that's making the repair. And then there's the cost of the road work in orange, traffic disruption in gray, in yellow, service disruption to customers who have their water service shut off, and then in light blue, the property damage. And I think it's fairly obvious that for most breaks, what you can see is that the direct repair costs are a very, very small fraction of the overall cost to the community when you have a water main break, When you add in the road work plus the direct repair costs, it's about 50% of the break for most breaks. And then the rest of those costs are really societal impacts that you don't feel directly as a utility, but things like traffic disruption, service disruption, and property damage. And certainly for your largest breaks, those societal impacts are much, much larger. So I think it's just important to understand as you think about the consequences of breaks that they go well beyond just the utility. So with that context in mind, what we're going to talk about today, I'll give you an overview of the Westerville distribution system. I'll talk about the importance of using really high quality data, because we do use some computer models to predict future breaks, and so it's the old garbage in, garbage out scenario. I'll show you how we use the utility specific data to develop the probability of failure forecasting, that prediction of when pipes will fail on a pipe by pipe basis. We'll talk about the consequences of failures, and we'll put probability and consequence together to show you how we determine what the risk exposure was for each and every pipe in the Westerville system, and then how we use that risk information and apply that to develop a replacement planning scenario that targets the riskiest pipes in the system. And then we'll go over the recommendations that we made for Westerville. It's a very linear presentation. Hopefully you'll be able to follow on fairly easy and see how this might apply to your utility as well. So first we'll start with the distribution system overview. This is a graphic that shows the era of installation of the water mains in the Westerville distribution system. So development starting in the 50s, ramping up in the 60s all the way to the height of development in the 70s all the way through the year 2000. And then it's been ramping down since then as the city has built out. So relatively young system by some standards, and we'll see sort of what the impact of that is in a couple slides here on pipe materials. So length of pipe, or excuse me, diameter of pipe in the system, predominantly 6 to 12 inch pipe with some 16-inch pipe as well. Based on the era of installation, you can see that the Westerville distribution system is made up almost exclusively of cast iron and ductile iron. So almost 99% of the system is just cast iron and ductile iron. Okay, so now we'll talk about break prediction and the importance of the input data and the review of that data. So one thing you'll notice here, I've got a screen capture here from a software I was talking with Victoria about right before we started the webinar. This software is called Infrasoft, and it is designed specifically for this purpose, for analyzing water distribution system data and break data to make predictions about when water mains will break. And so it's very easy to actually use this software. If you've got a GIS, you can basically just import your shape files for the water distribution system. Mostly what you need are very basic asset attributes. So era or year of installation, size, and material. You got those things in a shape file. We can get started. And then of course you import your break database as well. So as soon as you do that, you import those shape files into the software, you get this dashboard. And this dashboard is basically a quality control dashboard. It's going to show you the number of assets, the number of water mains that were imported. It also tells you if you have data quality issues with those. So for example, there are some checks on whether you've got a date of installation for the pipe. So if there's no date of installation, it would identify that 34 out of the 7,700 plus pipes didn't have a date of installation. 31 didn't have a material. There were 5 that had a bad diameter. There's a user-defined issue here where there was one pipe with a year of installation 1190, so I think that was probably 1990, just fat-fingered. So right off the bat, you can kind of see if you have any significant data quality issues. What we found with Westerville's data is that there weren't many issues at all. 0.5% of the pipes had issues. We have the ability to just ignore and exclude those pipes if we want to, and just move forward with the analysis and make predictions on the 99.5% that are in good shape if we wanted to. Or we could click into this and actually see if we want to resolve any of the data issues. So this would be really important if you're a utility that has data quality issues, more so than Westerville did. You can go ahead and in that dashboard, I can click on these 35 pipes that were identified with issues. It brings up a list of all of those pipes. It shows you what those issues are. I'm going to click on this one. This pipe right here had no material, and it brings up this interactive dashboard. The pipe in question is showed sort of highlighted in this magenta shade here, this highlighting, and I'm able to click on the pipes to either side. I was able to see that all three of these pipes, you can see by the labels here too, all three of those pipes were installed in 1951. They all had the same diameter, and so and the pipes on either side were ductile iron pipes. So I was able to click into this and change the pipe material from unknown to ductile iron for the purposes of the analysis. So again, as I mentioned, this wasn't much of an issue. I was able to do this manually for Westerville because there were only 35 pipes in question. So it made sense to go through, and we could go through on a one-by-one basis and try to resolve any data quality issues. We were starting, as I mentioned, with over 99% of the pipes had a known installation date, material, and diameter, as well as an asset ID. For data sets that aren't in such good shape, the software that we use, Infrasoft, has an artificial intelligence module that can populate that missing attribute data. So I know for some people, you hear the words artificial intelligence and machine learning, it kind of makes you cringe. They've been overused over the past couple of years. But I can tell you, in this particular case, all it's really doing is following the same logic that I went through in that example, where you've got pipes on either side with a known install date, same diameter. You can make an assumption there that you can fill in the material. It's going through that type of logic, and rather than having to do that 100 or 1,000 times if you've got a really bad data set, you can have the artificial intelligence go through the exact same logic for you and save you a lot of time. It will create a list of issues. It doesn't go back and update the GIS automatically, but one of the sort of secondary benefits of this process is we can take the data from Infrasoft, share that with the utility, and they can make a determination about whether they want to update their GIS as part of this project as well. Okay, I'm going to jump down to learning objective number 3. We're skipping 2 for now, understanding the importance of utility-specific data. So why is utility-specific data so important? I'm going to show you, this is for a different project that we worked on about a decade ago, and it shows for this system, which is a very large system in the Northeast US, it shows what the cost of a replacement plan would be for their water distribution system going out to the year 2050 and the year 2100. And you can see the size of that replacement program. This is based on using industry assumed expected useful lives for pipe. So you could say for ductile iron, maybe the expected useful life is 85 years. For cast iron, anywhere from say 70 to 80 years. Maybe for asbestos cement pipe, it's a lot less than that. But we just went out and used some industry assumed expected useful life values for that region and came up with this replacement program. Then what we did is we went back, we used the asset attribute data and the break data specifically for the utility that we were working with on this project. And this is what the replacement program looked like in light blue. So we went from industry assumed expected useful lives shown in black to the utility specific expected useful lives in blue. And you can see a 65% reduction in what that proactive replacement program looked like. So a reduction of $1.2 billion for them. And by the year 2100, about a $2 billion savings. So I will say this, this is not necessarily going to be the case for every single utility. It could be that you've got particularly fragile pipe and that light blue bar might be higher than if you had based your replacement program off of industry assumed expected useful lives. In most cases, in my experience, it is lower because those industry assumed EULs, in my opinion anyway, are a little bit conservative. So it's a big push for you to use your own data in order to develop your replacement plan. And again, you know, your pipes are going to behave differently as well based on a lot of things, based on who installed them, who the manufacturer of the pipe was, what are the soil conditions, do you have aggressive soils, you know, how do you operate the system and so forth. So just it's really important to use your data if you can. Okay, so let's talk about how we use that data now to make predictions about when pipes are going to fail. So this is some data. This is from Westerville, back to Westerville again. This shows the average annual break rate and based on the year. So starting from 1988 all the way up to 2019, you can see this break rate. Now, I would say even in 2019, 2018, when we did this project, it's not a significantly high break rate. In fact, it's probably about the 25th percentile in the US, but you can see this big change starting at about 2009, 2010, where it really started to accelerate, and that's what drove this particular project. So when we looked at historical breaks, what we found is because this system was predominantly cast iron and ductile iron, that there was only one break on all of the other materials. So in terms of using predictive software, we couldn't use that software for HDPE, PVC, copper clay, etc., because you can't make a projection, you know, based on 1 or 0 breaks. We really focused in on cast and ductile. In that particular case, for those other materials, you can go out and use the industry assumed expected useful lives. But for the 99% that's cast or ductile, we imported break data to start to form the basis for the predictions. Same type of dashboard comes up as part of the Infrasoft software when you import the break data. So you can, it looks at issues like, is the date of the break on the pipe before the installation date of the pipe? So something is wrong, obviously that can't happen. We found 4 pipes where that was the case. So it could just be that the pipe was replaced at some point, and so the installation date was updated, but the asset ID didn't change. We also wanted to exclude utility hits. So what we're trying to do with the software is predict the degradation of pipes. A utility hit can be excluded from that because it's just going to skew the results. We had a date of a break of 11/19/2019. That was after we started the project, so we knew there was a mistake there. And then we looked at a few, there were some duplicate breaks. So there was a break that it had the same pipe ID, the same date of the break, just had a different break ID. So we think in that particular case, I think we're able to verify that there were 5 breaks that were just entered twice. And so we were able to exclude those breaks from the analysis so we didn't skew the results. All of this is done. You can display all of this on GIS. It's the Infrasoft software talks back and forth with GIS. And so it can, in some cases, help you visualize where there are some clusters of breaks in some areas and where there are less in other areas. Okay, so let's talk about how we use that break data and determine which pipes are behaving really well and which ones might be representing the biggest risks and problems to the system. So we can see through the software there are a number of automatically generated graphics that we use to help us with our analytics. The first, we look for a relationship between the break rate and material. As you would expect, break rate is very heavily correlated with the material of the pipe, and we can see that here. We've got cast iron in green, ductile iron in red, and the bars, the height of the bars represent the break rate. So for cast iron, it's about 16 breaks per 100 miles per year, or 17 per 100 miles per year. And for ductile iron, it's about, well, a little bit less than half that. So just under 8 breaks per 100 miles per year. The length of the pipe is shown, or sorry, the age of the pipe is shown here by this line here. So we can see that the average age of ductile is about 30 years old. The average age of the cast is a little bit over 50 years old. So we looked at the break rate versus age as well. So we've got the age of the pipe on the x-axis here, the break rate on the y. And as expected, we were able to see sort of a trend in the rise in the break rate as the pipe aged. This is for cast iron specifically, but we wanted to just make sure that we're seeing these trends that we expected. We also look for a relationship between the break rate and the diameter of the pipe. Generally speaking, larger pipe has a larger wall thickness and therefore degrades at a lower rate and will have a lower break rate. And that's exactly what we found with the Westerville data as well. So 4-inch pipe on the left here has the highest break rate. A little bit of an anomaly here with the 8-inch pipe, but you can see the general trend is down. Break rate goes down as diameter goes up. So that was expected. So what we're able to do with this is we can, there are some sort of, again, pre-canned graphics that allow you to develop these, what we call aging curves, that show you how different cohorts of pipe are aging. So this particular cohort of pipe is small cast iron pipe with a diameter of 3 to 6 inches. And you can see what the correlation of age is versus the predicted break rate. We can develop these for large cast iron pipe. Same with ductile. This is a graphic that shows, rather than graphing the break rate versus age, we graphed it based on the year of installation. So the oldest pipe, going back to 1954, 1956, is breaking more frequently, of course, than the more recently installed ductile iron pipe. This is the relationship of the ductile iron break rate versus diameter. Same trend, where the larger the pipe, the smaller the break rate. And we can build these, we can show how different cohorts of ductile iron pipe are behaving. In actuality, what's happening behind the scenes on this in the software is that there is a specific probability of failure that is being predicted for every single pipe in the system. So you could go to an asset ID, go to a specific pipe, and it would tell you what the probability of failure is in 2020, 2025, 2030, all the way out as far as you want to look. Extremely powerful. When we bring that all together, we can make some predictions about what the break rate in the entire system will look like under the do nothing scenario, where you're not doing proactive replacement, you're just going in and repairing breaks. You can see that the break rate would rise pretty significantly, and that's what Westerville was really concerned about, like we talked about at the top, that they saw this rise in break rate. And what this says is from the year 2020 to about the year before the year 2035, the break rate was expected to double if nothing was done. So that's where the major concern was. All right, so let's talk about the other part of the risk equation. We talked about the probability side. Let's talk quickly about the consequence side. And so there are a lot of factors that impact the consequence of failure when water mains break. So the diameter is something that we look at because it's an indicator of what the potential property damage might be. It's an indicator of what the repair might look like. It's an indicator potentially of the number of customers that might be impacted by that break. We also look at proximity factors. This is just done in GIS. We look at different layers and how they overlap with the pipes. So are there intersections with roads, water bodies, structures, railroads, and other things that would increase the cost of the repair based on the complexity of the repair that would be done. And then we also look at hydraulic consequences. What I mean by hydraulic consequences is when you have to do the repair on that main, if you can't do a live repair and you have to isolate that main, you close the valves. The users that are on that pipe will lose water service. And so we can estimate what the impacts to them are as well. So hydraulic and physical consequences. So just kind of a look of how we do that. You know, we use a 1 to 5 scoring system for each of these criterion. So this is just an example based on the diameter of pipe. If it's less than 8 inches, it could get a score of 1, all the way up to a score of 5 for a 16-inch or greater than 16 inch pipe. So this 1 to 5 scoring system is pretty much industry standard through most asset management texts. This is how consequence of failure is often scored. Looking at adjacency to things like railroads, water bodies, or structures, you can set up similar criteria. So if you were looking at a water body, you could get a 0, or if the pipe is within 200 feet of a water body, you could get a score of 3. If it's within 50 feet, a score of 4. If it's intersecting, it would get a score of 5. This is roadway adjacency factors. So we say we score it based on the roadway classification. So if there's an intersection, or if the pipe is within the primary buffer of an interstate highway, it's going to get a score of 5. If it's in the secondary buffer, it would get a score of 4. If it was intersecting or within a primary buffer of a principal arterial, it would get a score of 4, and so forth. Scores go down as the classification changes. And then lastly, we can look at critical customers. Again, this goes back to hydraulic consequences. If you've got some critical users that are wet businesses in your city, you'll want to know about that, where they are, what pipes they're on. So examples are bottling companies. So when I worked for City of Columbus, the Budweiser manufacturing facility was by far the largest user, and they were the most significant customer. So major consequences if they lost water service. But it could be other wet businesses. It could be schools, could be hospitals, dialysis centers where water is extremely critical to their operation. And you can see how we gauge the impact based on what type of critical customer it is. Okay, we look at large users as well. This is the top 10 water users in Westerville, a summary of those top 10. And so the pipes that these customers associated with were listed as high criticality pipes. All right, so we bring that together, the probability of failure on a given pipe, which we know we can do on a pipe by pipe basis, as well as the consequence of failure score we can do on a pipe by pipe basis, so we can develop a risk score. I think most of you have seen this illustration before. It's fairly intuitive, but we've got likelihood on the y-axis, consequence on the x-axis, and obviously if you've got a high likelihood and consequence of failure, that represents a very high risk. If you've got a low likelihood and a low consequence, that represents a really low risk. And so you want to concentrate your efforts in the upper right-hand quadrants and in some of the other sort of upper right quadrants here, where you've got either high consequence, high likelihood, or both. How that translates to water main replacement is actually fairly straightforward. So if you'll ignore these green bars just for a second here, all we have here is the pipe aging curve, similar to the ones that I showed you before for ductile and cast iron pipe. So we've got the age of the pipe on the x-axis and the break rate on the y-axis, and this gold bar just represents how that break rate increases over time. So if this one specific pipe had a really low consequence of failure, let's say it had a consequence of failure of 1, consequence score of 1, we'd go up to this top green bar and we'd say, okay, it's got a really low consequence. I'm willing to accept a really high break rate as a result of that, say 100 breaks per 100 miles per year, or the equivalent of a break per mile per year. And I'd follow that green bar over, and where it hits the curve, it would tell me that for that particular pipe with a really low criticality, I would be okay replacing it at about age 145 years. That until that point, just doing repairs on breaks would be acceptable. Now, for the highest consequence of failure pipes, this could be the same pipe as we just talked about, but it's located in the central business district. It serves a bottling company. It's under a really significant roadway. So that same pipe with the same performance, we would not be willing to accept a high break rate on it. So maybe we would only be willing to accept 10 breaks per 100 miles per year. We follow that across, we hit the curve, we come down, and it says we should replace that pipe at age about 55. So we can do this for every single pipe. And when we do that, that gives you a replacement plan for every single pipe in the system. This is just a tabular way of saying what those green bars were. You know, you can adjust this. Each utility can adjust this, but it basically says we looked at consequence of failure scores from 1 to 20 and made a decision about what the maximum acceptable break rate was for pipes in each of those consequence of failure bins. And that's how we developed that graphic. So when we did that, we were able to, again, on a pipe by pipe basis, develop risk scores. This is just a figure that illustrates that. So you can see those scores here. In red, obviously the highest risk scores. Orange and yellow are sort of the high to mid range, and then the pipes shown in green are the low risk pipes. We took this a little bit further in Westerville's case, rather than just having consequence of failure scores in that 1 to 20 range. We used that Water Research Foundation study that I showed you at the very, very beginning, where they studied the true cost of water main breaks. And we were actually able to put dollar value costs on each of those breaks. We multiplied those the cost of the breaks times the probability to come up with a monetized risk score. And that becomes really important when you're trying to decide how much money you want to spend to replace pipes. Okay, so let's talk about some different replacement scenarios, and we'll kind of wrap it up after that, and we'll show you the recommendations that we made for Westerville. So if we just took the results out of the model, again, sort of using the probability and consequence data, going across, seeing where those consequence scores hit the curve and tell us at what age those pipes should be replaced. It shows a big backlog of replacements. And this is very, very typical. We see this with a lot of replacement planning studies that we do, whether it's for water mains or facility equipment. They tend to show a big backlog at the beginning. In this particular case, it shows a $3.5 million backlog, but then immediately it drops down to about the $500,000 range. So we know that this is not realistic. So we developed another scenario. We called it the normalized scenario, where we looked at the average cost over the next 25 years. Came out to be about $750,000. And this is what that replacement scenario looks like. These are actual replacements where we selected actual pipes. And so in green, you see the sum of length that we recommended be replaced in any given year. And then the gold line represents what the investment level would be in each of those years. Okay. We also looked at a scenario where we reduced the investment to, instead of about $750,000, we said, what if we reduce the average annual investment to $500,000? We wanted to see what the impact would be on the system-wide break rate over time, the number of breaks that would occur over time. So I mentioned before, we were able to, I showed you this blue line where we were able to predict what the break rate would look like if we didn't do anything at all. We took those 3 investment scenarios that I just described, and we said, all right, what will the break rate look like, or what would be the average number of breaks that occur in any given year with each of these different investment scenarios? So the baseline scenario, the one that had the big, heavy $3.5 million investment in the first year, the break rate goes way down. Number of breaks that would occur goes way down, and then it starts to rise again. The lowest cost, the $500,000 per year investment, which represented a 250-year sort of cycle to get through the entire system, you can see, for obvious reasons, it doesn't have as big of an impact on the break rate early on. But what we do see is a convergence, a pretty significant convergence around the year 2030. It starts to spread a little bit by the year 2035. But what this told us is that we really could get away with the lower investment level at the beginning. And then we can come back and reevaluate the reinvestment rate, or the investment rate rather, in the year 2030. So that is, in fact, what we did recommend. We recommended the 250-year replacement cycle. We know that's not sustainable. Pipes don't last 250 years. But what we did, we validated this recommendation. We were able to look at the data and show that by replacing 5% of the length, it would avoid 36% of the future breaks between now and 2030. So what's happening in the Westerville system is there are a few really bad actors, if you will, some really bad pipe. And if you address those early on, then you'll address a majority of the breaks, and then you can go back in future years and reevaluate the investment scenario. Again, the existing break rate is low right now, even though it's rising. And so that was also another justification for starting out with the lower investment rate. What we did after this project, as far as our recommendations, was we worked not only with the Public Service Department, but we worked with the Planning and Development Department, and we took our recommendations and we correlated those to future paving projects to try to make sure we aligned those projects together and avoided costs like repaving costs. So we're continuing, the city is continuing to track breaks. They're going to reevaluate the replacement strategy. At the time, we talked about reevaluating within about 3 years, which would be this year or next. And then the other thing that we talked about was changing some data management practices for abandoned mains. I really didn't cover this earlier, but if you think about it, if you're making predictions about, let's say, human longevity, if you wanted to predict how old we will all be before we perish, if you don't look at, if you only look at people that are alive today, you would make a prediction that we'll live forever. You need to include information about the people that have gone before us to understand when we might die. Now, you could also say, okay, well, I can look in the mirror. I see myself changing every day, so maybe I'm not going to live forever. So you can make predictions based on just looking at an active population, in Westerville's case, looking at the active population of pipes. But if you do have data on abandoned pipes, pipes that have been replaced, if you have asset attribute data for abandoned mains, and you have the break data associated, if you preserve that break data associated with abandoned mains, that's going to enhance the results that you get. And so that's something that I put the word out now to folks that are listening. If this is something that you're considering, this is something that you should think about as well, is preserving data for abandoned mains. And that's what Westerville has been doing over the past few years, so that when it comes time to do the reevaluation, they'll have more data to work through. So again, we just looked at these different investment scenarios. There was the baseline scenario. We looked at, ultimately, we looked at that 250-year scenario, as I mentioned, and it came out to be about $520,000 of investment. So why would you look at this advanced risk-based approach? Number one, more accurate projections, as we showed when you compare industry assumed expected useful lives versus using your specific data. Optimization of resources and savings. This, again, you could see we were able to justify a much lower investment. This type of this type of tool, the analytics that we did, obviously give you a lot of granularity, as opposed to just using 1 to 5 scoring systems for probability in particular, where some folks are using just a 1 to 5 scoring system to determine when pipes are failing. If you use this, our approach, and use this software, obviously you can get pipe by pipe probability of failure numbers, and that gives you a much better ability to prioritize where you want to go in and do replacements. We were able to explore different funding options, and I think one of the most important things is when you do this type of analysis, you've got a lot more confidence in your results. Your results are a lot more defensible, they're justifiable, and you can go to the powers that be, whether it's within your organization, or if you're going to a city council and requesting funding, if you need justification for it, this type of analysis provides it for you. When we worked with Westerville, actually they're a very proactive community. They're very data-driven and innovative community. Their city council was on board with backing a proactive water main replacement planning program. They asked the city, what should the budget level be? And they didn't really know. And I remember Dick Lorenz, one of the engineers at Westerville, saying, going through this process finally gave us the ability to provide that number to City Council with some confidence and to justify that budget. So that's another benefit of the program. So last but not least, my last slide here is something that I took actually from PWX 21 last year. Right before I gave this presentation, there was another presentation that talked about communicating. And the presentation said 65% of the population learns visually. We remember only 10% of what we hear, 30% of what we read, 80% of what we see. And that is just another bit of advice, I guess, for folks that are thinking about this type of program. Those failure curves that we were able to generate through the software, the aging curves, as well as the risk graphics and the maps and things like that, are extremely helpful in communicating up and out of your organization to justify these types of programs as well. So I'll conclude there. And Josh, I would be happy. We've got, I think, about 20 minutes left on the webinar. I would be more than pleased to take any questions that folks have.
Yep, thank you, Kevin. Very good presentation. We've got a couple questions that have rolled in here. The first one is the cost of water lost during a waterline break/repair included in your analysis?
Yeah, it's a really good question, and the answer is yes. And that's if provided we take those translations of consequence of failure and use those monetary costs that the Water Research Foundation provided. So that was one of those one of those very first slides that I shared. If I can go back to that. Can you see that graphic? I think you guys can see that graphic now.
Yes, we can see it.
Okay, great. So yeah, so what we did was we took the consequence of failure scores that we did do on a 1 to 5 scoring basis and translated that over to a cost curve that followed these values that were produced by Water Research Foundation. And I can tell you that these costs were inclusive of just about anything that you could think of. So they include the cost of materials, the cost of labor. They include the cost of the vehicles, the depreciation on the vehicles that go out and respond to water main breaks. They actually looked at the environmental impacts. If there were impacts to a water body, they looked at impacts to the atmosphere. If they were from emissions, actually that tends to be a really, really small number. But they also looked at, as I mentioned, things like resurfacing, repaving, or restoration of the site, and other aspects. So yeah, these costs are inclusive of just about any social, environmental, and financial factor that you can think of.
Thank you, Kevin. Second question here is, based on the data and analysis presented, can you make recommendations on the pipe materials to be used for waterline replacements and/or future waterline extensions?
Yeah, I mean, I think by taking your existing information, meaning your asset attribute data and your break data, you're going to see, again, you can look at the break predictions on a pipe by pipe basis, but I showed those aging curves. See if I can scroll down to some of those aging curves here. Right, so we had these aging curves that we showed for ductile, small ductile, large ductile. We had the same aging curves for cast iron. So yeah, I mean, based on the analysis and your understanding of how different materials perform in your system, then we could make some recommendations about what would be best as far as replacement material. I mean, there are some trends, obviously. If you go out and you look at either Bury No Longer, which is an AWWA publication. There's a Utah State study that comes out every few years on pipe performance by material. For most communities, asbestos cement pipe was a horrible decision. Ductile iron pipe in most cases is a very good decision, particularly if you have it lined on the outside. Factory, a factory liner or factory protective coating on the outside, I should say. If you've got aggressive soils, if you think you have aggressive soils, that would be something we would recommend. As if you don't have aggressive soils, you might not need to pay for the protective coating from the manufacturer. Although I think we've heard from a number of manufacturers that they may make that standard in the future for ductile. But yeah, certainly you can take a look at this data and figure out what might be a good replacement material. I wouldn't do it without looking at your data.
Next question here is, did your water main replacement cost calculation include all costs such as backfill, pavement replacement, water service replacement, valves, hydrants, etc.?
The cost that I showed, these investment costs at the end, when we looked at the different investment scenarios, the $500,000 level, $750,000 level, those were just direct costs. They didn't have the add-ons of engineering and mobilization, construction, administration, and so forth. So I think these costs ended up, we added about 25 to 30% onto those costs, if I recall correctly, to get the overall sort of soup to nuts cost to the city of Westerville. Good question.
And one thing I was hoping you could elaborate a little bit on is you had gone into that slide that kind of touched on all the costs associated with pipe replacement and brakes and all that. What costs were included in the service interruption?
Yeah, okay, so that's a great question. So service interruption, and actually I'll talk about a couple different ways that we can do that. So let me see if I can bring that up. So this is maybe a good way to explain that, Josh. So again, when you have a break and you have to isolate that pipe to do the repair, you're going to interrupt service to potentially a variety of different types of customers. If they're residential, the impact is typically small. It's obviously a lot smaller if you can notify them, right, as well, if it's a planned repair. But when you have unplanned repairs, the impacts can be fairly significant. And I would say, so we've got these types of customers in these different bins, 2, 3, 4, and 5. This is based on, again, this goes back to that Water Research Foundation study, where we actually called all of these types of customers, and we asked them the types of consequences that they suffered, if you will, or experienced as a result of an outage. So for example, a break that would impact a school. About 2 miles south of where I am right now is a middle school. I think it's called Hastings Middle School. And there was a break there a couple of years ago. It happened at about 7:30 in the morning, right after all the kids got dropped off for school. So we talked to their folks about what the impacts were. They had to, obviously they had to deal with shutting down water in their school and the consequences of that. They had to send kids, they had to close the school because they had no fire protection. So they had to send all these kids home, but you can't just put kids on a bus and send them home because you don't know who's waiting back at home. You don't even know if they can get in the house. And so you have to now notify, there's cost notifying all parents and guardians. They have to potentially take time off from work. So we included those costs. They had to pay the teachers, custodial staff, and so forth. They had to pay the busing staff, and et cetera. They had to make those payments and they get no value out of it, right? So in that particular case, we estimated the impact as $75,000 in financial costs when we monetized that. When we looked at hospitals and dialysis centers, we went into those kinds of impacts as well. And so those cost numbers, those consequence numbers where we monetize those came directly from those types of customers and the experiences that they had and the actual impacts that they experienced, based on that Water Research Foundation study. So I'd say it was pretty inclusive, or at least there was attempt to capture as much of that data as we could get.
Thank you, Kevin. Next question here is, what length of water main replacement did the asset management plan recommend for Westerville, and what percentage of the total system? If you have those numbers on the top of your head.
I can show you, actually. If we go back to the different investment scenarios. So this is at least where we ended up with the recommendations. And so again, we ended up with this investment level, about $500,000. Again, we tacked on some additional costs, ancillary costs to that. But what doesn't change on this slide is the length of pipe that we recommended. So the average length of pipe was right about a little over a mile, say. So you can see in any given year what the recommended replacement length was. And so most of the bars fall sort of right around that 1 mile per year of replacement. In some cases, it was a little bit higher, and in a lot of cases, it was just a little bit lower than that. I think one point on that, Josh, too, it just kind of triggered a memory when we did this presentation when we were in St. Louis. Director Kevin Weaver was there. He's the Director of Public Service at Westerville. He was there, and he said one of the other values that came from this study wasn't just understanding what pipes to replace, but what pipes not to replace. And so there were a number of locations where paving was taking place. Some had taken place in recent years where the Public Service Department said, you know what, we don't think we should replace that pipe, even though maybe in prior years they would have felt a little bit more comfortable if they had done the replacement of the water main at the same time as they did the resurfacing. But they made some decisions to say we're not going to replace those pipes, and we're going to maybe wait until the next paving cycle 15, 20 years down the road. And this data was able to help justify that. And I think that's a really common thing that folks get a lot of pressure, whether it's politically or otherwise, or maybe it could be a financial decision. You're trying to make a determination about whether to replace mains, when you do paving projects. And so this can give you the tools not to do that. And when you think about what the cost of one water main replacement project is, having good data and having the ability to say yes or no in those particular scenarios will pay for itself, very, very quickly.
Well, thank you, Kevin. That seems to be all the questions that we've got rolling in here. So with that, I will extend a thanks to the audience for watching the presentation. Kevin, thanks very much for doing this for APWA and LTAP, and we can go ahead and call it a wrap.
Thanks, Josh, and thanks everybody for tuning in. Really appreciate the opportunity. Take care.